Good morning, everyone. Today I'll be presenting on a very important topic in artificial intelligence, that is planning problem in AI. Planning is one of the fundamental abilities that make an AI system intelligent. It allows machines not only to act but to decide what actions to take to reach a goal efficiently. Our presentation today focuses on five key objectives. First, we'll understand what AI planning really means. Second, we'll define what constitutes a planning problem. Third, we'll look at the core components of a planning problem. Fourth, we'll explore the various planning methods and algorithms. And finally, we'll discuss the real world applications and challenges of AI planning. Introduction to AI planning. AI planning is a fundamental area in artificial intelligence that focuses on decision making, specifically how an intelligent agent determines a sequence of actions to achieve a specific goal. It has a versatile applications ranging from robotics and logistics to autonomous vehicles and intelligent games. In short, wherever there's a need for goal directed behavior, AI planning plays a vital role. The indispensable role of planning in AI. Intelligent behavior. Planning enables AI agents to exhibit truly intelligent behavior, moving beyond simply reactive responses to proactive goal achievement. Decision making and optimization. It provides the framework for optimal decision making, allowing systems to find the most effective paths to their objectives. Real world AI foundation. Planning forms the crucial backbone of sophisticated AI systems deployed in real world scenarios, ensuring robustness and reliability. Deconstructing a planning problem. Now, planning problem outlines how an intelligent agent can achieve its goal in a given environment. It is fundamental and defined by three key elements: initial state, goal state, and set of actions. The specific configuration of the world at the beginning of the planning process comes under the initial state. Then, the desired configuration of the world that the agent aims to achieve is known as the goal state, and the collection of possible operations the agent can perform, each with defined preconditions and effects, are the set of actions it is going to use to achieve the goal state. The ultimate solution to a planning problem is a coherent sequence of these actions that transforms the initial state into the goal state. Now, here is an example of robot navigation. Consider a simple scenario where a robot needs to move from one location to another within a room. So, the initial state, the robot is positioned at the door. The robot needs to reach at the table, which will become its goal state. And the available actions can be to move from door to the hall. The robot moves from the door to the hall, and then another move can be hall to the table. The robot moves from the hall to the table. The successful plan is the precise sequence of these moves that guides the robot from its starting point to its destination. Visualizing the state space. To understand AI planning, we first visualize the state space. Each shape highlights an aspect of how states in a system can be represented, analyzed, and used for decision making. Here's the breakdown. Represent states. System states are illustrated as nodes and are the foundations of state space visualization. Show transitions. States are connected with arrows and depth to lead to another. Identifying patterns. Recurring sequences with the state transitions are recognized. Analyze relationships. Connections among different states are studied to understand dependencies and behaviors. Predict outcomes. The system is used to forecast possible future behaviors based on current and past states. Make decisions. Insights from all the previous steps are applied to make informed and strategic choices. This process is continuous. After decisions are made, new states are represented, transitions are shown, and the cycle begins again. By identifying patterns and analyzing relationships, AI system can predict outcomes and make decisions. It is a continuous process. And after every decision, the system observes the new state and replans if it is needed to again ahead. Dissecting the core components. Every planning problem can be broken into four key components: initial state, where the system starts; goal state, where the system aims to achieve; actions with preconditions and effects. This describe what can be done and what changes occur; solution plan, the sequence of actions that leads from the initial to the goal state. These elements form the foundation of any AI planner's reasoning processes. Now, talking about planning as a search problem. AI planning can also be viewed as a search problem, where we explore different possible paths from start to goal. Common algorithms include breadth first search, explores layer by layer, guaranteeing the shortest path in terms of action count. Depth first search explores as deeply as possible along each branch before backtracking. A-star search, a powerful heuristic search algorithm that uses an estimated cost to reach the goal, making it efficient for complex problems. Heuristics search, general term for algorithm that use domain-specific knowledge to guide the search processes, reducing the search spaces. The choice of the algorithm depends on the problem's characteristics, such as the size of the state space or the optimality requirements and the availability of good heuristics. Types of planning problem that can be classical or partial ordered. Classical planning. In this, we assume a total ordering of actions suitable for straightforward scenarios, or partial order planning, in which we allow flexibility in action execution ideal for complex scenarios. So here, it operates in deterministic environments where actions have predictable outcomes, assumes full observability in the word state, suitable for well-defined problems with clear start and end states, like a chess game. In partial order planning, it allows for planning actions without enforcing a strict total ordering. Actions can be executed in any order as long as the preconditions are met, more flexible, and effective for problems where parallelism or interleaved actions are possible. The power of AI planning structured problem solving for intelligent agents. AI planning brings several advantages. It provides structured problem solving, helping to organize complex challenges logically. It enables automation, especially in robotics and intelligent systems. It offers scalability and efficiency, handling large scale problems effectively. That is, planning algorithms are designed to tackle large scale problems, optimizing resource allocation and operational throughput across diverse domains. And most importantly, it optimizes agent performance, allowing AI systems to act more strategically and with fewer errors. Representing planning problem. The Stanford Research Institute Problem Solver, that is also known as TRIPS, is a classic formalism for representing state and actions in AI planning. It simplifies the description of action effects. Each action in TRIPS is defined by three key components. Preconditions, that is, conditions that must be true for an action to be executable. Add list, a set of facts that become true after the action is executed. Delete list, a set of facts that cease to be true after the action is executed. Planning domain definition language. In planning problem definition language, it is the de facto standard language for expressing AI planning problems, enabling researchers to share and compare plannings to set the goal state. Standardization provides a common framework for describing planning domains and problems. Key elements are used, and versatility, that is, it supports various planning paradigms, including classical, temporal, and hierarchical planning, and research and competitions to extensively used in academic search and international planning competitions to benchmark planner performance. Search and problem solving. It consists of heuristic search algorithm, which is crucial for efficiently navigating the vast state space of planning problems. They employ domain-specific knowledge or learned estimates to guide the search towards promising states. The classic block word example. A classic illustration of AI planning is the block word problem. Here, an agent manipulates blocks to reach a specific arrangement, like stacking block A on block B and block B on block C. It's perfectly demonstrate the concepts of states, actions, goals, and transition in AI planning. That is, pick up A, robot picks a block A from the table, assuming it's clear, and then it stacks it on B. So robot stacks block A on top of block B, assuming block B is clear now, and robot picks up the block C from the table and stacks it upon block C, achieving a new configuration. Therefore, the blocks are now stacked in the target configuration, that is C on A and A on B. Challenges in AI planning. Despite its strength, AI planning faces several challenges. There's state space explosion as variables increases, possible state grows exponentially. Uncertainty, real world actions don't always go as expected. Incomplete knowledge, agents may not have full information about the environment. And practically, real time constraints and integration with other AI systems make AI scale larger planning complex. Case in point, planning in robotics. Let's take a real world example, an autonomous robot vacuum cleaner. Its planning goal is simple, to clean the entire room and return to its charging station. But it must continuously plan paths, avoid obstacles, and decides when to recharge, all while operating independently. That's AI planning in everyday life. The horizon of AI, future of planning. Integration with machine learning, real time adaptive planning, and autonomous decision making in smart systems. Combining planning's logical reasoning with ML's pattern recognition for more robust and adequate learning capability of AI agents. Developing and planning systems that can continuously develop themselves to monitor, replan, and execute. And empowering smart cities intelligently. Outcomes of this study: understanding planning problem definition, knowledge of classical versus advanced planning, and awareness of challenges and applications. Recognize the inherent computational difficulties and the vast array of practical uses across various industries. The real world application, again, is self driving cars. In self driving cars, these are one of the most advanced uses of AI planning. They perform route planning to decide the best path, behavioral planning to make the driving decisions like overtaking or turning, and motion planning to generate smooth, collision free movements. Each layer depends on real time decision making and rapid replanning. Essential references in AI planning is Russell and Norvig, AI a modern approach, a foundational text covering all aspects, including comprehensive sections on classical and modern planning techniques. Galab Now and Traverso. Automated planning, theory and practice, a dedicated resource providing in depth coverage of automated planning algorithms and their practical implementation. Relevant AI research papers. Stay updated with the latest advancement by exploring peer reviewed articles from conferences like AAAI, ICAPS, etc. Navigating the challenges and limitations of AI planning. Computational expensive, that is, the search space for optimal plans can grow exponentially. Therefore, we need computational demands and long processing times. Dynamic environment failures. Traditional planning struggles in highly unpredictable or rapidly changing environment where pre-computed plans quickly become obsolete. Reliance on accurate models. The effectiveness of planning hinges on the precision of the domain model. Inaccuracies can lead to flawed or unimplementable plans. AI planning is everywhere. In robotics, it is used for path planning and task scheduling. In space exploration, it powers Mars rovers to plan movement and analyze data autonomously. Across industries, it's helping automate logistics, manufacturing, and even medical diagnosis. Conclusion: the horizon of AI planning. To conclude, AI planning is the backbone of intelligent behavior. It enables machines to think ahead, act purposefully, and adapt intelligently to new challenges. As AI continues to evolve, planning will remain central to innovations in robotics, automations, and autonomous systems. Thank you for your attention. I hope this presentation helped you understand how AI planning forms the foundation of intelligent systems, making machines not just reactive but truly strategic thinkers. Thank you.